So this is actually some work that I did as a graduate student at UEA and as a postdoc at Princeton. I was working on this project that was funded by the Navy to study how rays swam. And that seems kind of funny, right? Why does the Navy care about how rays swim? Well, the truth of it is that rays and other animals can produce, we can use the mechanisms that these animals use in order to produce devices that can swim more efficiently than our current underwater vehicle technology, and can also do so in a very stealthy manner. They can sound like a fish, so that makes them very hard to detect. So the Navy is actually very interested in this problem, and so we received funding over about 5 years to work on this. So in the process, there are lots of fun things which I'll show you. So to start off, these animals, not just rays, are absolutely amazing to see swimming. This is at the Georgia Aquarium in Atlanta. If you get a chance to go there, they have this enormous tank where you can just sit here and watch these things. I mean, I can sit there and watch these things for days probably, just seeing how incredible they are. You see whale sharks in there, you see manta rays, there are stingrays, cow-nose rays, and this is a fun little video where that ray is extremely agile. And so I'm actually going to back this up, do this again. If you look in this tank, when you're looking at the rays, especially the manta rays that you see here, they look very lazy, right? They look like they're just kind of cruising along, they're not doing very much, and that's the truth of it, they're not doing that much in this case. But in the other video that you saw, you can see that these animals can be quite agile. They can produce a lot of force very quickly if they need to. And so these animals are quite amazing animals in terms of their performance. They can beat our current underwater technology in terms of accelerations, in terms of efficiency, cruising speed, it can win as well. So they're quite impressive. Now, I was lucky enough as a graduate student to get paid to go dive in Micronesia with these rays. So that's a very unusual situation, and it's hard to see from this image, but this is actually one of the images we had down at 80 feet. And so I'm sitting there, I'm not sure if you can tell, but that is me. And we're filming these rays, and in this case there are two manta rays. And these rays are swimming it's a wide open area, but they're swimming in this area which is relatively flat, and there's this rock outcropping where there are these cleaner fish. So these cleaner fish will come up and take parasites off of the rays. So they can come into this region and swim around. So we stuck this calibration device in the region to give us kind of a dimensional scale for how big these animals are, and we can use that to measure, for instance, the kinematics of their motion with absolute values. So we did that here in the wild. We were able to capture not only kinematic motions of their fins, but also the turning performance that they use in this area. So with that data, we were interested in saying, okay, if we can measure how these rays are swimming, at least the kinematics, what can we learn about the fluid dynamics? So in order to do that, I developed a computational tool to actually study how rays swim. And what I'm showing you here, it's not a ray, but I'll show you a ray in a second. This is just a computation of a pitching panel in this case. And this is an in-house code that I wrote. And for those of you who've taken aerodynamics, the 3 of you in here, or 2.5 of you in here, that have taken aerodynamics, this is actually a potential flow code. So in class, when we talked about putting little sources into a flow and seeing how that disturbed the streamlines, and talking about how we can create bodies with these things, this is that stuff in action. So this is actually, we distributed sources over the body, we distributed doublets over the body, doublets over the wake, and we can actually model these unsteady swimming problems. So this is something that in aerodynamics, for those of you who are going to take it, you'll learn the basics about this. We won't be doing this. Not yet, maybe 2 years from now, maybe we'll do that. But you can do some nice computations with that. So using this potential flow solver, we actually looked at different rays and how they swam. So this is a simulation of a manta ray, and what you see on the ray is actually the coefficient of pressure. And so red is actually low pressure and blue is high pressure. For those of you who took the class, you see blue right on the nose, that's a stagnation point for the ray, and you see red coming up on the fin tips, and that's a region of suction, actually. So just by looking at this visually, you can tell that the majority of the thrust that's being produced by these rays is out near the fin tip, and it's in the form of leading edge suction. So it's actually being sucked forward, if you want to think of it that way. And what's happening behind the ray is the wake structure. We call that the wake in general. And you can see that there is stuff happening in the wake. So now we can actually go back and identify more clearly what's happening. We can use things called vortex identification criteria there's Q criteria, there's then 2 criteria. What these do is they distinguish where vortex structures are in that wake. So these purple things are vortices. And these are actually forming closed loops. So there are these vortex rings that are interlocking. No. Okay. I'm going to do something, because this is pretty cool to see. Give me 1 second. Aha. That one. Okay, I think this should work. Yes, did work. Okay. So this is actually what it looks like three-dimensionally. You can see that these vortex rings are these interlocking rings that are being shed from those fins. And what's happening is these vortex rings are little tornadoes. And so these vortices are spinning around, okay? And if we actually take a slice and look at, we'll just take 1 slice through these rings, we can plot something known as vorticity. So that actually tells us essentially the rate of rotation of the fluid, okay? So you see here this blue vortex, and blue is a rotational sign that's going to be clockwise, and red is going to be counterclockwise. And so when we cut through the slice of this vortex ring, you see that in the center between those 2 groups of vorticity, there's a nice jet that flows backwards, okay? These jets, you can think of them as threading through the holes or the vortex loops in this case. So it's this wavy jet that's coming off of the back of the manta ray. And what's interesting about that is that this is just like a jet ski. What these rays are doing is they're producing these vortex structures that are accelerating fluid backward, and that's producing this velocity jet. And since we're adding momentum to the fluid, we're going to produce a force, and that force is our thrust. And that makes itself evident on the fin when we see that low pressure zone, that suction near the leading edge of the fin tips. So that's the basic mechanism that these rays use to swim. It's also seen in stingrays. So this is a stingray simulation, and it's a little bit harder to tell. I'm not going to show you all the details about the stingray simulation, but if you dissect this as well, you find similar vortex structures that are produced, these interlocking rings and velocity jets near the fin tips as well. In this case, actually on the body, we're not plotting pressure. This is actually shear stress, and usually I use this figure for something different than what I'm showing today. But anyway, that's shear stress on the body for those who wanted to know. So, question that I had at the time was, okay, we see stingrays swimming, we see manta rays swimming, which one's better at swimming, right? Which one can swim more efficiently? And that's a question that the Navy's really interested in. If we're going to develop a device, which animal do we explore in terms of its fluid mechanics to produce a device? We want one that swims efficiently. So this is a plot of something we call cost of transport, which I won't get into too many of the details, but basically, this is an inverse of miles per gallon, okay? And it's normalized by the amount of mass of the object. So, if a really big object, it's going to be a lower value, but this is a metric that we typically use for energetics. And so, what it's saying is, how much energy does it take to travel a given distance per unit kilogram for that animal, okay? So if that number is low, that's good. The lower the number, the less energy it takes to swim a given distance. So when we look here, there's several things up on this plot. We have cost of transport, which is our energetics, versus swimming speed. And I have simulations for the Atlantic stingray, simulations for the manta ray. There's also some simulations as well as real data from some commercial devices that are up there. So the first thing to notice is that if we're comparing the stingray and the manta ray, you'll see that the stingray here has a very similar range of cost of transport as the manta ray. Okay? So effectively, a stingray and a manta ray takes the same amount of energy to swim the same distance when you normalize by the mass. Okay? But you'll notice the manta ray does it about an order of magnitude faster. right? They can do that swim using the same amount of energy in a tenth of the time. So what's interesting about that is it tells us essentially that the manta ray is effectively a better swimmer. It can get from point A to point B faster using the same amount of energy. But perhaps this isn't a very fair comparison because stingrays, if you think about it, they typically are swimming along the substrate, right? And being in the presence of a solid boundary like that has effects. So the question is, what happens if we rerun these simulations for stingrays swimming along the ground, right? Then what do we see? So this is something we typically call ground effect, right? And we talked about this a little bit at the very end of the semester in aerodynamics. There's some really cool aircraft built on this concept. And normally, when we're talking about ground effect, everything we know, nearly everything we know until our paper recently, was on steady ground effect. And what we don't know much about until recently was unsteady ground effect. So the Lund class chronoplane was one of our, I think it was one of the coolest planes of the day that we had. And it's a ground effect vehicle. It's designed to fly near the surface of the water. And by being close to a solid boundary like that, or in this case not so solid of a boundary, the fluid field is modified. It does two things. It increases the lift and it decreases the induced drag. And so the combination is you have a more aerodynamically efficient vehicle. So there are other aircraft built on this concept. You see the Sea Eagle there, this other strange vehicle here, another seaplane. But in nature we see this as well. You see brown pelicans, they'll come and swoop near the water surface. You'll see skimmers that go over the surface as well. Bats do this. But all those devices and animals are taking advantage of steady ground effect. But what happens if we have a ray? So these rays, they're flapping their fins. And they're flapping their fins near the substrate. You can see the fin tip gets pretty close to the substrate in this case. This is a pretty small ray though too, as you can tell. But nonetheless, they're operating pretty close to the ground. When you flap your fins like that, there are unsteady fluid dynamic effects that take place that we, until recently, didn't know much about in the case of the ground effect. So, since we didn't know anything about it, we can get away with doing a very simple model. So, instead of actually doing the computation of a real ray, we said we're going to be like other fluid mechanicians and we're going to make this ideal. We're going to choose something very simple to work with. And we're going to learn our basic principles from the simple computation and device. We have both experiments and computations. And we're going to translate our findings into what it means for a stingray. So, this is our simple case. So, first off, to keep things simple, we made it two-dimensional. We don't want three-dimensional things. Life gets complicated. We can do it, but it's more challenging. So, we have this simple two-dimensional airfoil here, and we were oscillating this airfoil about that pivot point that you see. And we place this airfoil near the ground, some distance d away from the ground. It has some chord length c. We're oscillating with an amplitude a. So there are a couple inputs to this problem and a couple outputs. So we're looking at some non-dimensional inputs in this case. The ST is our Struve-Hall number. Basically, we're non-dimensionalizing our frequency. A star is our amplitude to chord ratio. D star is our distance to chord ratio to the ground. So these are the parameters that we vary. We vary these by physically varying frequency, we vary amplitude, we vary the distance to the ground. And these are our outputs in aerodynamics. We talk about different force coefficients. These are our force coefficients. We have coefficients of thrust, coefficients of lift, coefficients of power, and we have our efficiency. So just to give you an idea, thrust is our force in the x direction in this case. So the amount of force we're going to produce in the streamwise direction. Lift is perpendicular to the streamwise direction, and power is the amount of power we put into the fluid to produce these forces. And then the efficiency as well, the efficiency, right? How efficiently we're taking that power and translating it into thrust force. So we, at Princeton, we set up some experiments there. So this is a schematic of our flow channel that we have. And in this flow channel, we did two things. One, we had this pitching panel, this hydrofoil here, and this thing would be pitching about that pivot point that I showed you. And we'd be flowing water over it, and so it did two things. One, it would directly measure the force production by the pitching panel, and the second thing it would do is we could actually shine a laser sheet through the water and illuminate particles in the water. By doing that, we can actually track the particles over time and calculate the velocity field at every time instant. So when we talk about velocity fields in fluids, if we're actually doing it experimentally, this is how we do it. We actually measure the fluid, the flow field directly using this PIV type of setup. So there's an interesting note here, which, sure, I'll talk about it. I wasn't sure I was going to talk about it. I'll talk about it. For those of you who are interested, there are boundary layers in this problem on the wall. They're about half a quart length thick. And that's an interesting side note to keep in mind for later down the road. We use this nice potential flow method where we have doublet panels, wake doublet panels, and we wanted to look at the presence of the ground. Right? So to do this, we use a method of images to enforce our boundary condition. And we talked about this very briefly in aerodynamics, about how you can explain away some of these ground effects by doing a method of images type of analysis or thought experiments. And so this is physically what we did. We had our panel, our physical panel, the upper panel, and it would be flapping, and there would be an image panel, which is really a non-physical mathematical artifact that just flaps in a completely out-of-phase motion, and all the circulations are exactly the opposite rotation. Okay, by doing that, we enforce our boundary condition and ensure that we have a boundary present, essentially. So here's a nice video of this thing flapping. So this thing is flapping in essentially infinitely far away from the wall. We're 1,000 chord lengths away from the wall, so we're effectively infinitely far. And so in this case, we are flapping this, or pitching this panel up and down, and you can see what I'm plotting in color is vorticity. When I'm plotting in terms of the velocity vectors, or is the velocity field. And you can see what this is classically known as a reverse von Karman vortex stream. So we get these vortices that are shedding at every half cycle, and you can see the velocity that they're inducing between the vortices is creating this undulatory jet, like I described before. So that's adding momentum to the fluid, which in turn causes a force forward. So in this case, we've taken the same set of parameters, except now we moved in close to the wall. And in this case, we moved to a d star of 0.5, so half a chord length to the wall. By doing so, you notice that the wake looks different, right? And which way is the jet angling in this case? Upwards. Upwards and backwards, right? So we've now shifted our velocity jet. What would we expect to happen in this case? Any ideas? A straight back jet produces a force on the body that goes forward. What about an angled jet?
Some will push it down.
Some of it will push it down, exactly. We're adding momentum not only backwards but also upwards. So that's be a reaction, an equal and opposite reaction on the object downwards and forwards. So we think that there should be some lift force, or negative lift force in this case, being produced. So we'll see that actually in a second. But first, we didn't just do this computationally. We did this experimentally as well. So these are experimental images. These are PIV images from our flow channel over in Princeton. You'll see on the left here, we're infinitely far away from the wall, and you see the reverse von Karman vortex stream, just like we saw in the computations. In this case, at a d star of 0.5, half a chord length from the wall, you see the angled jet, the pairing of these vortices, that's now moving away from the wall. And here's a comparison between the two. The top row is the experiment, and the bottom row is the computation. And if you take a look at this, there's pretty good agreement. There's some things that are different, right? You see that the vortices, the vortex 1 is forming a little bit later in time. You see the vortex 2 is forming, and the 1 and 2 are pairing up. And in the third frame, you see that they're advecting away from the wall. But what's really different is the angle of the advection away from the wall. You see that the computation has a vector between those two vortices that's more upward than the experiment. And the difference there is actually that boundary layer thickness. So it happens to be that we're actually inside the boundary layer. And if you're in a boundary layer, you're sitting in rotational fluid. And it happens to be that in this case, the sense of rotation is in a clockwise fashion. So that rotational fluid is actually rotating the vortex pair of the experiments to rotate more in the streamwise direction. So we see that difference because of the presence of the boundary layer in this case. But we can explain this pairing mechanism using our simple method of images arguments. So we have our physical vortex, vortex 1. We have our image vortex, vortex 1 prime. Okay? Now each one of these vortices induces a flow field around it. And we describe that in aerodynamics too. So what happens is when these are free to move, they move with a local velocity field. So if vortex 1 prime is going to induce a velocity back on vortex 1, the direction that it will affect, or that it will induce a velocity, will be upstream because of the sense of rotation of vortex 1 prime. That's going to cause vortex 1 to slow down. It's not going to move downstream as fast. So because it slows down, at the next part of the phase, when you form vortex 2, it's now closer to vortex 2. So those two actually pair up, and vortex 1 induces a velocity on vortex 2 upward and backward, and vortex 2 induces a velocity on vortex 1 upward and backward. So the two pair up, and they shoot off from the wall together. And so because of the presence of this mathematical object 1 prime, it actually causes vortex 1 to lag in real physical space, and it causes it to eventually pair up with vortex 2. And that's the pairing mechanism that we see occur continually in these ground effect experiments. And this mechanism really is an invisible mechanism, and we can explain what's happening just with that alone. So it tells us a lot about what's actually going on in this case. So the question originally was, okay, so we saw these angled jets, that must mean that there's some lift being produced. So here's a plot of a bunch of curves, right, a bunch of different colors. What do they all mean, right? So if we look on the vertical axis, we have coefficient of lift. On the horizontal axis, we have essentially frequency. It's non-dimensional frequency. So we're talking faster on the right side of that graph. And the dark blue case that you see right along the 0 line for coefficient of lift is when we're infinitely far away from the wall. So without a wall present, we produce a velocity jet only in the streamwise direction, and we're only going to produce a force in the horizontal direction that's a reaction force. And there's no, in the time average, and I should say this, to be technical, it's actually a time average lift coefficient. We don't produce any lift force in the time average. And so that happens no matter what frequency we operate at, and that's the blue line that you see there. If we now are operating at a d star of 1, so we're now 1 chord length away from the wall. So if this is our panel, we're now 1 chord length away from the wall, we actually are getting a lift force. But this lift force is below the 0 line. This is a negative lift force, right? So the force is actually pulling the object down to the wall. It's sucking it down to the wall. As we get closer to the wall, d star of 1/2, we see that purple curve. Here's d star of 3/8, even closer, and even closer, d star of 1/4. You'll notice that as we get even closer to the wall, the lift changes. It goes to a positive sign, right? So that means as we get even closer down to the wall, we have a lift force pushing us away from the wall. So between these 2 points, or between these 2 regimes, there's a region where we're being sucked down, and if we get too close, we get pushed away. So there's a stable equilibrium point between those 2 regimes. And so that's, I think, a really interesting finding that we figured out. So what this can suggest is that when these rays are swimming, they do so in a way that maybe doesn't take a lot of control energy. They swim near the ground at a point where perhaps there's a stable equilibrium, where this naturally gets sucked down and then pushed away at some stable point. But the other question is, what happens in terms of thrust? Does this get better? Does this get worse? So here's a plot of our coefficient of thrust, time average thrust, versus this non-dimensional frequency, this true Hall number. The blue curves are, well, the red curves are d star of infinity, so infinitely far from the wall. The blue curves are when we get close to the wall, a d star of 0.38. And the lines represent the computations, and the points represent the experiments. And there's clearly a difference between the two, and that has to do with having skin friction drag turned on or off, which I won't get into that detail, but we know why that's the case. But what's important is you can see the difference between the red and the blue, whether it be experimental or the computations. And you can see that at a given frequency, or Struve Hall number, if we go from very far from the wall to close to the wall, we get an improvement in our thrust. So in fact, we get around a 44% increase in our thrust. So for a ray, what that means is they produce more thrust, they can swim faster in that case, at the same frequency. They hold that frequency constant, and when they get close to the ground, they swim faster. What about power? How much power does it take? So over here we plotted our coefficient of power versus our frequency, non-dimensional frequency. And again, the blue is close to the wall, red is far from the wall. And we see that looking at the red curves and looking at the blue curves, that the blue curves are higher than the red curves, right? So our power also increased in the same process. So even though we're holding our frequency constant, as we get close to the wall, we swim faster, but it's costing us more energy to do so. So overall, you can plot the efficiency, which is essentially the combination of these two parameters. Now, there's one thing I want you to ignore in this curve, and that's the black line. Forget the black line, I'm not going to talk about it, okay? The other lines are computations, and the points are all experiments. Blue is, again, close to the wall, and red is very far from the wall. So if you just look at the computational lines, not including the couple of dashed lines that are there, all the other lines, red or blue, fall on top of one another. If you look at the experiments, and you look at the red colors and the blue colors, and you try to distinguish some trend among them, you don't really see a trend. There's really no obvious trend. Red's not always lower than blue, blue's not always higher than red. So, in fact, those numbers, the experimental error, there's really no difference for the experiments. So when we look at this data put together, the blue dash curves are something special. They're really, really, really close to the ground, which is a whole other effect. But besides those curves, what we see is that our efficiency doesn't change if we get close to the wall. So even though it's going to cost more power, we're going to swim faster, and ultimately that means you're swimming with the same amount of efficiency. So that's a good thing if you're a ray. You get to swim faster, and your efficiency is the same. So if we go back to this original performance curve, we have our Atlantic stingray over here, we have our manta ray over there. We have the other stuff, which is not too important for today, but what's important is that if we took the Atlantic stingray and if we actually ran the simulation, which to be fair we haven't done yet, some future work for us to do, but if we ran a simulation of the stingray near the ground, what we'd expect now with our results on ground effect, we'd expect the stingray to swim faster. We'd expect the cost of transport to stay the same because the efficiency is going to be the same, but those lines should move closer to the manta ray. My guess is they won't move all the way over to the manta ray, but we have yet to find out. So, if anybody's interested, you can talk to me. Maybe we can think about running some simulations on this. So, that's what I wanted to talk about today. Here are what I presented are the basic mechanisms for ray thrust production. They produce these interlocking series of vortex rings that produces a velocity jet in the streamwise direction, and that causes a reaction force forward, the thrust force. If the rays are operating in ground effect, or if devices are operating in ground effect, you produce these characteristic angle jets that angle away from the wall. We can explain those with inviscid mechanisms, method of images. And there's a nice stable equilibrium in the lift force, which could relate to where stingrays actually swim in the wild. And ultimately, thrust is enhanced, and it costs no extra efficiency to do so. So if we wanted to develop devices, this is a way to make our devices swim faster without necessarily spending more energy. So that's all I have for you guys today. That's some of the things we've learned about rays. There are some more and some more details I can discuss with you anytime if you have any questions.